Yellow.
Hello?
Hey, do you hear me?
Yeah, I can hear you.
Okay, awesome. Yeah, this little crazy head mount thing is working.
Okay.
So what's up?
So I tried doing the chapter 7 quiz, the 7 quiz about what we learned yesterday, and I didn't really understand the questions that asked about probabilities.
Okay, so what do you want to know about probability?
Like the he was doing calculations with like with z-scores, I guess. Z-scores I'm kind of confused on. And then about getting the z-score into going into your book and finding the z-score and then finding the probability.
Okay. Okay, so I'm going to show you. I guess first we should probably go over what z-scores are, right?
Okay, yeah.
Okay, so we can get any let's just start from this point, right? So usually when we talk about scores, we just call them x, right? So we just say, well,
Okay.
here's the score x, and lots of times we'll say that these scores x follows some normal distribution, or sometimes we'll write x follows a normal distribution
Okay.
u sigma.
Uh-huh.
But the idea is the same. The idea is that, okay, x scores fall on some distribution. That means there's some middle value that's more likely because the height, right? Like that, this here is the probability of something occurring. So it's like when we're in the middle, these values are much more likely because there's just a lot more points here, right? So that blue is more likely than oh no, got my marker. So then if this purple is the same width, there's just a lot more area in
Uh-huh.
the blue than the purple, right? Because the point is that there's more observations near the middle.
Yeah.
So that's what we get from just raw scores, just talking about where scores land. So the reason we want to use a z-score is that if you wanted to calculate something like this, like let's say these are IQ scores, I don't
Mm-hmm.
want to ask you how many people or what probability is it that a person has an IQ between, so in the center with IQ it's 100. So if I say what's the probability of someone being between 100 and let's call it 120. So really what I want to know is what area is this, right?
Mm-hmm.
Like that's the nature of the problem I'm asking you. And what we want is we want to make our job easier, because the real way you solve this is that this normal distribution can be described by a mathematical formula, and you can use calculus
Uh-huh.
to get you this area, but we don't want to do calculus, right? We want to basically
Okay.
do easy stuff.
Yeah.
So what we can do is turn our score distribution, which has a center at 100, standard deviation in this case, we'll just say it's 15, which is for IQ. So that describes this thing. But if we want to solve problems, there's actually one distribution we can use, which is we call the standard normal distribution, which looks just like this. So it's the same data.
Uh-huh.
But the difference is that this center here is now no longer 100. This center is 0. And
Okay.
one standard deviation above is 1, and one standard deviation is -1.
What's the name of that graph?
So this is just right here. This we call this a normal, and
Uh,
this one it'd be the standard normal.
okay.
So it's standard because it's standardized in that the the reason we call it standardized
Uh-huh.
is because it doesn't matter what numbers we're measuring up here, right? Like this could be height, this could be IQ, this could be depression scale, anything that follows a normal distribution, we
Uh-huh.
can draw it like this, but the center will be dependent on the measure we're taking. So if it's height, the center is 5'9.5" for men, I think 5'6" for women. But
Okay.
that's the problem. It basically makes it so we have to solve things. So instead, what we want to do is transform these scores into this distribution, because
Okay.
this distribution is the one that's described by the z-table.
Mm-hmm. Okay.
So what we're going to do first is we want to turn our x score into a z-score. And so it's actually really easy to do this. Like the math is really simple. So you just have to know basically the formula for a z-score. So z is just equal to some x value minus the center value over the standard deviation.
Okay.
So we can calculate all these things. Like usually when we give you a problem, we'll say, okay, we'll say x bar is equal to 100, sigma is equal to 15. So we'll basically give you this thing and this thing. Then you just plug in the x and do the math.
Okay.
And what's nice that comes out of this is, so what happens if, so right here I told you the center is at 100 and the standard deviation is 15. So what's your z-score if you have an x score of 100?
0.
Yeah. So that is why our 100 turned into 0.
Oh, okay.
Because the z-score is basically saying take whatever your center is and do a transformation to it such that the center will be 0.
Okay.
The same way when we go one standard deviation above. So if I told you your x score is 115, what's your z-score now?
Is it -1?
Um,
Because you do 100 minus 115 divided by 15.
oh no, so here I'm saying your x score is 115. So it's actually 115 minus 100.
Oh, I think it's because the board for me is flipped.
Oh, your board is flipped? You're seeing it the opposite way? Okay, then let me flip it back because I know I turned on a flip. I wasn't sure if it's necessary. Okay, does that make more sense?
Yeah, I can see it now.
Okay, that's weird because on my screen now it looks flipped, but I guess it's fine for you. So, okay, yeah, I wasn't sure which way to do it. Okay, so yeah, so here's what's happening. So, yeah, we're giving you an x score of 115, and then we subtract the center of the distribution, which in this case is 100.
Yeah.
So then what's your z-score?
1.
Yeah, so if you had a score here of 115, that now turns to 1.
Oh, okay.
So now no matter what, as long as the original data, the x-scores followed a normal distribution, when we turn them into z-scores, now they will look like the standard normal distribution.
Okay. And so for the standard normal distribution, the x-axis is like the z-score.
Yeah.
Okay. Okay.
And then so the way you solve these problems, like if I say what's the probability of someone having an IQ, okay, so here's an easy one. What's the probability of someone having an IQ greater than 100?
50%. 50%.
Yeah, so that's a no math way, right? Because I'm just basically splitting the thing in half. And I've told you to assume that it's a normal distribution, which means you can be safely say, well, half the people are better or higher than 0.
Okay. Got it.
And so the way you're using the table is I could say how many people have scores between 100 and 115.
100.
So then I want to find the z-score for 100 and then the z-score for 115.
Yeah.
Which is, right, so when it's 115, it's 115 minus 100. Or actually, this is supposed to be 100, right? So that's the thing we did earlier, which is 100 minus 100, 0, score 0.
Yeah.
115, that's 115 minus 100 over 15, it's 1. So all that's telling you is we have 2 points now in the standard normal. And then the way the table works, so I can actually probably pull up the table we're using. Oh God, where is it? Yeah, the table will tell you either the probability from the center to some known point,
Okay.
or sometimes it'll say from this known point to the end.
Okay.
So if you wanted to find out,
It'll be like 1 to negative infinity, or negative to the negative side. It'll be like either 0 to 1 or 1 to the end point.
yeah, usually it'll be that way because the thing is symmetric. So essentially, right, 0 to 1 is the same as 0 to negative 1.
Okay.
So I'm actually probably, the slides I have planned for tomorrow, I can actually show you some of them.
Okay. And so
Because
then you would just add. Sorry, what?
Oh, because I'm basically gonna solve these with the class tomorrow, but
Oh, okay.
let me show you right now because
Okay.
it's what we're gonna need to do. Okay, so I'm gonna screen share now.
And so basically what you did was you add like the z-score of 100 to the z-score of 115.
Well, so it's not so much adding, it's more okay, I'm back. So what it is I want to find basically, like, once I have all the data, what I really care about is this. I want to end up at this point. I want to be able to say, okay, now I'm working on this known distribution. The standard normal has a center at 0. And I want to know essentially what point of it do I care about? So if I asked you from the x of 100 through the x of 115, that is the same as asking you z0 through z1.
Yeah. Okay.
So then looking at this normal distribution, I'm just trying to find this area.
Oh, okay.
So I can use a table to say, okay, from 0 to whatever the number is. Like in this case, it's easy because it's 1. So from 0 to 1, what's the probability? Like how many scores appear here? And that'll just be some number. I think it's like probably 34%.
Okay.
So here in that case, if you would just look up the z of 1 and say how much areas between 0 and 1, and that is really your answer. That answer says that's how many people you would expect to find. So if you grabbed all people at random, about 34% of them will be between an IQ of 100 and 115.
Okay.
And that's based on the fact that this standard normal distribution is already really well described by the z-table, so we don't have to do any calculus. Essentially, somebody just solved all the points on this distribution. They solved the calculus of them and then just wrote down a table for us.
Okay. Cool.
We're essentially using the fact that someone's already answered what the z is from 0 to 1 or 0 to 0.9 or 0 to 0.8, whatever the thing is we're trying to figure out.
Okay, got it.
And sometimes they get more complicated, right? Because I give you the easy case of saying 0 to 100, but I could have given you, so what's negative 1 z-score?
Negative 1 z-score, would that be 75? An x-score of 75?
85, right? 100 minus 15, is that correct? Yeah.
Oh, yeah, sorry.
Yeah,
I did 25. Yeah.
Yeah, I was also confused too.
Yeah.
But yeah, so in that case, I could have given you, here's a z of 0, and I'd say, okay, get me from negative 1 to 1.
Yeah.
And usually what I would tell people, well, in this case, it's really easy because it's the exact same number. You could just figure out whatever this is, right? That's x, that's some proportion. And then x times 2. 2x, right, would be both of these pieces.
Yeah.
But in other cases, let's say this was 0.5, right? I just say whatever number ends up being 0.5. So it's 7.5 below 100.
Yeah.
So then you just break the problem into two pieces, and you essentially solve from 0 to negative 0.5 is some probability, call that x.
Yeah.
You can call the other one y. X plus y is the answer.
If it asks for negative 0.5?
Yeah, if it says, okay, how many people have z-scores between negative 0.5 and 1?
Oh, okay.
Because here we're saying, essentially, we want to solve from negative 0.5 to 0 because we can use the table for that, and then from 0 to 1.
Okay, so sometimes you have to break it up into pieces, basically.
Yeah.
Okay.
So that's really the most complex things you're going to have to do with z-tables is I'm going to give you one that isn't just find one piece, but essentially find a range that crosses the midpoint. And whenever it crosses the midpoint, it usually ends up being easier to say, let's say I'm on the left and the right of it, and I can say, okay, well, figure out whatever this area is right here and figure out this rest of this area. Or sometimes, I'll say how many scores fall above negative 1 on the z-score. So if the negative 1 is the z-score we're looking for, I want to know from here to infinity.
Yeah.
So then in this case, you could solve it two ways, right? You could say 1, which is all the probability, subtract, and we'll just call all this purple area here x, right? So if I say 1 minus x, then it's everything that's left.
Yeah. How would you find x?
So you could look up 0 to negative 1 would be some number. In this case.
And then 1 minus that, right?
Or, well, 0.5 minus that, right? Because we're only talking about half of the...
Oh, yeah.
Because this is always only going to add up to 0.5. Both sides are going to be 0.5.
Right. Okay. Got it.
Yeah, I think the z-score stuff is important to understand because pretty much all the stuff we do coming after is going to be very similar to z-score. What's going to change are these specific things that go in.
Yeah.
But the general form of the z-score will basically be maintained through the next stuff, which is just this. So it's not so much so this is the actual math of it. But conceptually, I think it's more important to understand that the z is just saying some score minus the middle or the central tendency measure,
Yeah.
divided by whatever the spread of that thing is.
Okay.
So later we'll change, the scores will be different things, or sometimes the middle will change, or sometimes the way we calculate the spread will change.
Yeah.
But in essence, this general form basically holds up for the next few things we're doing in class. So if
Okay.
you really get the concept of this is giving us a standardized distance.
Yeah. Okay. And then my last question was just in class, the professor mentioned how there's like different like percent probabilities depending on like the range of your standard deviation. Like if you're one standard deviation away, it's like likely that like 30% of the time it'll happen between that I don't know how to explain it. Do you know what I'm talking about?
Yeah,
Like,
it's like
he's
this,
like he was
right?
like it's like 34, 34, 16 or something. I forget.
Yeah, so usually we give you these rules of thumb. So from -1 to 0 is about 34%,
Okay.
and which means on the other side it's also 34%.
Right, because it's symmetric.
Yeah,
Okay. And this is only for normal distribution though, right?
for the standard normal.
Standard
Right,
normal.
because our original data were also a normal distribution, but the center was at 100, so we couldn't use the table.
Okay.
So that's
So,
basically the only reason we're doing z-scores, is to be able to get us onto that table so we can look up values.
okay.
But otherwise, there's infinite tables, right? Every time a distribution has a different mean, we need to make a new table.
Hmm.
Instead, we can turn any normal distribution into the standard normal by using z-scores, and then we can just look up stuff.
Okay, so you can only use like these rough like percentages if it's a standard normal distribution.
Yeah.
Okay.
Although, so not exactly. What it
Okay.
really is you can only use them if you're talking about standard deviation units. So in the normal distribution, we
Okay.
can say between 0 and 1,
Yeah.
but this could also be between mu and sigma, or mu and plus sigma, or mu and minus sigma, right? Because our original, we said mu was 100, or I think I gave you x bar, but it's the same thing, basically.
Hmm.
Or sigma is 15. So the area between 0, or -1 and 0 is the same as the area between 85 and 100 of raw scores.
Okay.
So if in your head you can realize, like, okay, if I tell you this distribution with a center of 100, standard deviation of 20, and I say how many people will get scores between 100 and 120, if you recognize, oh, that's one standard deviation up, then about 34% of people will be there.
Oh, okay, got it. So it's for standard deviations. Okay, got it.
Yeah. It's just that in the z-score, one standard deviation is 1 unit.
Okay.
By definition. That's why we actually call it the standard normal. The standardization is turning it so whatever your standard distribution is, we convert it to the number 1,
Okay, cool.
or it's
Thank
worth
you.
1 unit along the z table.
Okay, thank you so much. That was all my questions. Thank you.
All right, awesome. So I will probably be covering these more in depth tomorrow during section,
Okay.
because I know this is the thing that everyone always gets stuck on. Like,
Yeah.
what the
It
hell
was
are
just
we
like a
talking
big
about?
jump, kind of. But
Yeah,
yeah.
it seems to come out of nowhere, but I think we should be okay by the end of the weekend. I think.
Okay, thank you.
No problem. Take care.
Bye.
Bye. Okay, so I got a question about this slide here. This is slide 14 from day 5. And so the person was asking, why is it shaded to the right and not to the left? And I think you can see what I'm drawing here. So the only reason it's shaded to the right and not the left is the actual question we're asking. So at the top, he's saying, so this is shorthand, this P and then a paren just means this is the probability. Like I want to know the probability of some event. So I guess I can switch this back off. So here's how probability works. Like you write, if I want to know the probability of rolling 6 on a dice, I would say probability of 6. So that's usually like the shorthand we use to describe just the probability of events happening. So here on the slide, what he's actually asking is what's the probability of disgust being greater than or equal to 61.65? So he wants to know literally like what's the chance of getting a score this high or greater? And so what you're doing here is you're just turning 61.65, which is, this is X, the red is basically the same scale, but in scores, like raw scores. And below it are the Z scores, the Z score equivalents. So going from 44, which is the center, that's the equivalent of a Z score of 0. So we go up one standard deviation of 20 points. We go from 44 to 64. But in standard deviation units, we go from 0 to 1. So the only reason the right side is shaded is because we want to know what's the probability of disgust greater than this given point. So from here, if these represent all the scores, right? So this standard normal or this normal distribution represents the probability of everything happening. So the area under this curve sums to 1. That means this curve can capture the probability of every event happening or every given score happening. So we just want to know, well, of all the scores that are going to happen, how many of them will be greater than some value? So that's why we ask the probability of disgust greater than this number. And so you just get this number and find this area. That's why it's shaded to the right, because we're trying to solve for the right side. We want to know how often will we get scores that are greater than 61.65. And so what you're doing is you just take that one score, turn it into a Z, and then you can use the Z tables to help you figure out what this actual probability is. But conceptually, the reason it's to the right is because we want to know how many scores are greater than that value. All right, cool. It seems to have answered the question, so I'm going back on mute. And if you have more questions, I'll be back. Okay, I was just asked another question about the same day, so day 5, slides 39 and 40. And essentially the question is like, what the hell are these? So I think the point we're trying to make here is that, so n equals 100 means we're going to draw a sample of 100 people. And what we're trying to show you is that in statistics, you're never going to get the same thing. So even if I sample 100 people, that sample of 100 people won't always produce the exact same numbers, right? Just by random chance, I happen to get, let's say I'm sampling people on their IQ score. Just by random chance, sometimes I'm going to get a group that's smarter, or sometimes a group that's not as smart. So the means will move around. Or, let's say this group, it's early in the morning, it's 8 a.m., you're going to bomb the intelligence test because you're tired. So there's lots of things that are going to vary within your samples. And the point is that as you keep taking different samples, you see every time we get slightly different answers. So we get 44.78 or 42.49, and these are just different means. So here we're saying assume there's an infinite population of people, and I'm just pulling out groups of 100 and calculating their averages and plotting here the frequency of how often each of these scores occur. But I think the point he's trying to make is that every time you do this sampling, you get slightly different numbers. And this relates to the bigger topic in class, which I think is a really important one to get, which is the difference between the score distribution and the sampling distribution. So, right, we have X scores that follow some distribution, center at mu, standard deviation +1 sigma, -1 sigma is that way. So this is just saying if I took individual people from the population, right? There's a person here, another person here. Over time, if I take enough observations, the shape of that distribution will look like this. But that's saying, like, I can use this to tell you what's the probability of, if I grabbed a person at random, that they have an IQ score between, this point and this point. And I can use z-scores to calculate what that probability is. But that is the probability of an individual person being in this range. So some of the stuff we've started talking about in class is the idea that lots of times I'm not really interested in how often do individual people fall within range. And what I want to know is how often do groups fall within this range. So here we would say the X scores follow a normal distribution. They have a center at mu and a spread of sigma. But lots of times what I want to know is, okay, if I took a group of 100 people, all right, let me make the math easier on myself. If I took a group of 16 people, how often, where will their means fall? So of this population of people, I pull out 16 scores, right? So I go, here's my little group of scores. I've just sampled random people, putting them together, and I can calculate some average score for them. So then this here is the sampling distribution. And what the sampling distribution tells us is here is how often we're going to get mean scores within a given range. And the sampling distribution, so now we're not plotting X scores, we're plotting X bar scores, because every time we take a group of 16, we get a X bar score, right? We can calculate an average for that group, and then we can plot where that average is. So let's say we get the first person, they're here. That's one X bar score. And then we do this infinitely, right? We want to know, what does the shape of this distribution look like? So if I took another X bar, it's a little higher because, right, the slide's showing us that we're going to get different means every time. So here's another mean. And over a while, these start taking their own shape. You just keep taking X bars over and over and over. And what you get is something that looks like this. So the center here is still mu. So this sampling distribution is centered around the same point. But what's different is here. Instead of using sigma, is what we did before, to represent our, what we called it before was the standard deviation. Here, actually, so if we say the X bar scores, they follow a normal distribution. I've told you where the center is. It's still at mu. But what's changed now is how these scores spread out. And this is actually sigma divided by square root of n. So X bars follow a normal distribution, center at mu, And the spread is sigma divided by the square root of n. And the reason this happens, right? So all you have to think of, sigma is just some number. We just give it to you. So if just look at any fraction. So let's say this is 100. So now we're going to change the size of the group we're pulling. So if I pull a group of 1, right, square root of 1 is 1, and I get a standard error of the mean, which is what we call standard deviation with, right, so this is equal SEM, standard error of the mean. This is just how the means will spread out. So that's the only thing that's changing. So what's happening here, when I take a group of 1, it's actually the same as just looking at raw scores, right? I'm just saying, pull me a group size of 1 person and describe where that person's score is going to fall. There's not really a reason to do an average with 1 person, right? They're just the only score. So it's going to look exactly like up here. But what changes is, let's say I take a group of 16 people. So it's 100. It used to be divided by 1. Now it's going to be divided by 4. So now this number, which used to be 100, is now equal to 25. So up here, the raw scores will spread out, right? We've just said sigma's 100. We just made it up in this case. So we've said, okay, the raw scores are going to spread out. It's going to be 100 units above the mean to be 1 standard deviation up. But our mean scores here don't spread out nearly as much. And the reason is that if I take a group of 16 people, it's very unlikely I'm going to get a group of all tall people or all short people or all smart people or all dumb people. I'm going to get a mix of people. And as I get bigger and bigger groups, those groups will be more and more like the population every time, right? You can imagine if you're in a classroom, if you pull 2 people at random and take their height, those pairs of 2 people will produce heights that are much more different than each other than if I split the class in half and took the heights of each half of the class. And so that's all this is trying to capture. Like the fact that we're taking whatever the score spread out by and dividing by the square root of n is trying to capture the fact that as n gets very large, from one sample to another, the scores will be very close to each other. So if you look again at the slide, that's the point he's trying to make. When you have a sample size of n equals 100, we don't get the exact same average every time, but look how close these are. 44.78, 42.49, 41.67, 44.85. They're all like a pretty tight range of scores, where the raw scores themselves would spread out much more. I'm trying to see if he gives an example of the raw scores. He doesn't. But basically, the raw scores here end up spreading out a lot more because of the fact that it's only 1 person, right? From person to person, we can have a lot more variability than we would have if we're taking groups of 100 people. If you take 100 people and average them, it's very unlikely that if you take another group of 100 people, you're going to get a radically different response. Or if you take 1 person or 2 people, you could get radically different responses, right? So if I'm measuring your height and I happen to sample 2 people off the UCLA basketball team, their mean height will be very tall. But if I sample 200 people, let's say I sample 2 basketball players, right? I get a mean height of 6'4". What are the odds that if I sample 200 people from UCLA, I went out on Bruin Walk and grabbed 200 people, that their average height would be 6'4"? It's much, much smaller because of the fact that as you get bigger and bigger groups, you're just going to get more mixed amount of people. You're going to end up with short people, tall people, and they'll end up kind of canceling each other out and giving you scores that are much more similar to one another as you take continual groups of that size. So I think that's the only point he's trying to make, is saying, like, one, recognize that every sample will give you a slightly different mean value or center value. But the thing to recognize is that if we plotted where all of these mean values end up, based on how big our group size is, they will be much, much closer to each other than the raw scores themselves. So these raw scores up here can vary a lot because from one person to another, I can really see a lot of change. But when I'm taking large groups of people, the change will become tighter and tighter. So if this is, let's say, a group of 2, right? So this is 100 divided by square root of, actually it's square root of 4, because that makes it easier. Then I just have it. So this is going to be half as wide when the group size is 4. And then if I go to a group size of 16, now instead of having 100 divided by 2, which was 50, which is what I got when I had 4 group size, Now I'm taking 100 and dividing it by 4, which gives me 25. So again, I have half the thickness again. So these things become more and more peaks. So if I take a group, let's say of, let's give me another one, 64, right? So square root of 64, that's 8. So it's 100 divided by 8, some number that's much smaller. And now this group is looking more like this. So the point is that this thing is coming in like that. It's getting tighter and tighter based on the fact that I'm taking larger and larger groups. So that's why the sampling distribution, which describes where we would expect our samples to fall if we pulled them from this larger population. And the shape of this is going to be largely determined by the size of the group we're pulling. So we pull really huge groups, we get things that look like this, right? Everyone is really close to the mean, because if my group is 2,000 people, I'm going to get a very, 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 very similar estimate of the group's average height from one group of 1,000 to another. Whereas if I'm pulling groups of 2 people, I might get something that looks like this, because it's like I accidentally pulled 2 basketball players, I pulled 2 like jockeys or whatever, or I pulled 2 people of regular height. So it's much more likely I'm going to get 2 people around regular height, or one tall person, one short person. They cancel each other out. But it's also very possible to pull 2 tall people, right? So 2 short people, they get an average that's right here. But if I take 1,000 people, I'm never going to get 1,000 all short people and no tall people to cancel them. So that's why when I pull a group of 1,000, it looks like this. Because essentially, when I pull 1,000 people, they're going to end up all over the place, and they'll all average out to something very reliable near the center of the distribution. So I think that's the whole point he's trying to make here, is that recognize each sample is going to give you a different mean, and that the spread of your means is much tighter than the spread of your raw scores. And it's because of the fact that you're sampling whole groups at a time and not just saying, okay, give me one person. So up here, you're able to answer questions like, what proportion of the population is greater than 5'10"? Where down here, you'd be able to tell me, if you pulled a group of 100 people, what's the probability that that group's average height will be greater than 5'10"? Which is a very different probability than just getting an individual person who's greater than 5'10". So hopefully that explains everything. Otherwise, I will jump back. All right, I'm calling that time, and I will see you all tomorrow.